Welcome to Yong Tuition. Today, let's talk about the speed of the wave, in particular, the difference between the so-called phase speed and the group speed. Because last time I shown that the speed of matter wave is actually half of the speed of the particle associated with this matter wave. Obviously, there are some conceptual discrepancies in the original idea of matter wave proposed by de Broglie. Some people may argue that if we just use the group speed instead of the phase speed, that discrepancy will disappear. So let's talk about this issue in more depth today. By definition, the phase speed or the speed of wave can be simply written as Vp equal to the product of wavelengths multiply the frequency. So this formula can be rewritten as frequency divided by 1 over lambda. Now, if you multiply 2 pi on both numerator and the denominator, we got a slightly different form for the phase speed. In textbook, these two new variables are defined as omega and k. So omega is the angular frequency, while the k is defined as the wave vector or wave number in the case of one-dimensional wave. That is 2 pi divided by lambda. What is a group speed of wave? Well, group speed of wave, the group speed of wave refer to the speed of a certain motion in the superimposed wave from many different sine waves. By definition, the group speed is equal to the first derivative of omega to the k. So that is why I rewrite this formula into the omega and k. Obviously, if you just follow our first line of the formula, we can simply rewrite this definition as a df over d 1 over lambda. If we just multiply the Planck constant h, we got this new form because constant h is constant. Okay. Now from here you can see, perhaps I use a bracket here. From the Planck's formula for the photon, for the energy, and the de Broglie's formula for the momentum. So this formula can be rewritten as dE and dP. E is energy and P is the momentum. Okay. Now, in the case of the single particle, so in the case, so if you have the particle move with mass with the momentum equal to mv, and the kinetic energy, it's also the total energy equal to p squared divided by 2m. And the velocity is simply p over m. So that is a simple relation we can obtain by using a particle model. Now, if you substitute this formula, in particular the energy formula, then we will get that if we this would be the d ddp. That would be p squared divided by 2m. Then you will get p over m, which would be exactly the speed of this particle. Okay. So that is how that if you use the formula for the group speed instead of the phase speed, then you can argue that the wave speed is the same as the speed of the particle. So this is the matter wave. So they move, if you consider this wave move at the speed of group speed, it's Vg, and that formula shown that the two speeds are identical. So there would appear no such discrepancy. However, let me discuss this in more detail. The group speed is not associated with a single wave. Okay, how can we produce? How can we observe the group speed rather than the phase speed? Then we have to introducing the concept. It's called wave package. It's called wave package. Sorry. Wave packet. A wave packet is as a result, is a formation of the wave packet is due to the superposition of many individual waves. For example, they have many tiny waves, and all of a sudden you will see the envelope built up. And if you go to detail, you will see that this envelope is a superposition of many individual waves. Okay, so this is called wave packet. And the speed of this wave package is actually represented by the group speed. Okay. So, but how do we form this wave package? Mathematically, we have assumed that the formula for the wave package can use psi. This is as a function of x and time, can be formed by superimpose. So you can either use integral or use a sigma form. Can we use a sigma form? So have superimposed different components of wave with different amplitude. The amplitude will be the function of the ki, and perhaps we can use a continuous form. We can, let's just use this form for time being. So ki, and that would be, can we use the exponential form of the wave? That would be ei, and that would be the phase. Okay, and the phase, what is the phase? Oh, this is a phase. Can we use phi to represent the phase? And that I is a variable from 1 to a large number. So large number could be as large as infinity. So in this case, actually, we can use integral to describe this phenomena. And the dk, so k is a variable now. K is variable, and the magnitude is a function of the k. K is continuous variable now, and then multiply these individual harmonic. That is would be what would be the k x minus omega t. Okay, so the reason to introduce the k vector or k number is that we can just rewrite 2 pi over lambda as a single letter. Okay. So that is the integration. The k came from the 0 to infinity. So you can see mathematically, this is a formula to describe a single wave packet. Okay. Now, how do we actually derive the formula for this formula here? How can we prove that the wave packet propagate as a function of time forward at this particular group speed? Then we have to do the first derivative by definition. So from here, we can see that this is called the phase, actually, the phase. We just write the phase here. So the phase can be written as phi equal to kx minus omega t. That is by definition the phase of wave. Okay, in this case, k change continuously. Okay. So in order to find the group speed, we have assumed a particular case when this the so-called stationary phase exists. So we just first found the first derivative with respect to the time. So we got we just found this not with respect to time, with time of k, rather. So let's do first derivative. So d phi divided by dk can be written as k dk is equal to unit. That would be d omega and dk multiply t. So this is the first derivative of the phase. Okay. In order to obtain the so-called group speed, we must let this first derivative equal to 0. So in this particular case, and we are talking about the so-called stationary phase, stationary. So not all phase can be well defined, the group speed. Only the phase became stationary can we define the speed, because based on this condition, the first derivative equal to 0, we can obtain that x is indeed proportional to the time at a certain velocity, d omega dk multiply the t. So that can be simply written as x equal to v group speed multiply the time. So in this way, the packet in this case is actually moved toward the right-hand side indeed. So you can see that this is just like the formula for the constant, the displacement at constant velocity. But from this description of the so-called group speed, you can see that we have to form the packet. We have to consider so many different waves, okay? But the original idea of the matter wave, first proposed by de Broglie, is so simple. It only indicates that the single wavelength, right? So therefore, by using wave packet to explain the speed of matter wave just for the sake of argument, it's nonsense. Okay, the discrepancy is still there, limiting the speed of the matter wave is only half of the speed of the particle associated with this matter wave. Okay. Next time, I will talk about why people use wave packet to explain the wave behaviors of the particle. Okay. And today I've just to demonstrate that, and we cannot use the group speed to show that the speed of the matter wave is exactly the same of the speed of particle. Okay, have a nice day and goodbye.